Can you guys hear me fine?
I can hear you.
Great. Yeah, sometimes the mic doesn't work on my webcam. Sometimes it does. I haven't deduced exactly the variable in the problem yet.
Hey, before we get started again, Professor,
Yes.
I don't know if you saw, but the homeworks are set to be due in 2019, so they're all past.
Don't worry about it. When I haven't made it a bit.
Got it.
It's from last year's course, so
Okay.
once I set the due date for them, I'll
Okay.
it'll be correct. So.
Will there be a quiz up this Friday?
Yeah, I'm gonna post it after this lecture. So.
All right, so we can do that right after this class if we want.
Yeah, anytime. And once you start it, you need to complete it within that specified amount of time.
I see.
So. Okay.
Mày mua giờ á, mày phải chạy đi mà. Money.
Helen, please mute unless you have a question or anything. All right, let's continue. So we'll do one more problem from this section. I think we'll leave that one out there. All right. We'll use cars again. So this is example 13. We'll do. Look at 11 and 12 at home. They're interesting examples. Try to work them out before you do it. And no problem, Helen. You'll probably see my kid running around here soon. So. All right, so there's a car that's going a certain speed, and the certain speed is above what the law states. So the car, we say that the car, we have a speeding car, sure, red, let's make it a red sports car. All right. And it's speeding and it passes an officer. The officer's waiting for the car to come. And he starts accelerating as soon as the car passes him. All right. And here, let's take the reference point to be in the center of the car. Let's not worry about the size of the car in this problem. Right? And initially, the car is going as fast as it can go. So it's going 150 kilometers per hour. The acceleration is 0. When we start at time 0, when the car, what we call time 0 is when the cop car starts to move, right? We'll call that position 0 as well in terms of distance. So when the car starts to move, right, the problem starts when these 2 points overlap. We have the cop car. I'll do it in blue, right? X naught is equal to 0. Over here, T is equal to 0. The V naught of the cop car, I'll put it as police, VP. I'll make it bigger. If you see something that's too small, just let me know, please. This is VP 0 naught, so this is not PO, P naught. Right. or actually the way they wrote it in the book is this. And then this is, and we'll call it S for the speeder. So any parameters associated with the speeder will have an S next on the as a subscript, and then over here for the police we'll have a P. Right? And we say that, and it asks how long, like this, 0. The question is, how long until the police catch up to the speeder? So let's figure out some things. So let's see what we have and what we don't have and what we need, right? So first, we'll have 2 equations of motion, right? Well, let me finish the drawing. And then, so until a time t when, when this occurs. So we'll have 2 equations of motion, right? So write them down. We have the equation of motion, the position function for the cop, right? I mean, for the speeder. Let's do the speeder first, right? So this problem starts at x0, that's 0. So then this is 0, right? And then there's a certain velocity that we start at, v naught 0. Then we have time. And then the acceleration is 0. So this is also 0. Right? So then all we have is this equation for the speeder. Let me put a subscript over here. Then for the police, this is 0. Oh, well, the position is 0. The initial speed is 0, right? And then we have the acceleration. And this ends up just being equal to the acceleration. So how many unknowns do we have? So this is the equation for the police. And I'll just rewrite the equation for the speeder underneath. Right. So how many unknowns do we have? So what do we know from so from here? We don't know t, right? What else don't we know? Do we know a?
No.
No, it wasn't given to us. What else do we know the position? The final position? No. No, right? And then what about for here? We don't know t and we don't know the final position of the speeder, right? So we have how many unknowns? 1, 2, 3, 4, 5 unknowns. So let me write that. XP at that time. XS at that time, T, we don't know, and A. These are the 5 unknowns we have. How many equations do we have? 2, right? We only have these 2 equations. So we need 3 more equations, right? Now, in this problem, they kind of say, using simple, so let me read the problem. So a car speeding at 150 kilometers per hour passes a still police car, which immediately takes off in hot pursuit. Using simple assumptions such as the speeder continues at a constant speed, estimate how long the police car will overtake the speeder. Then estimate the police car's speed at that moment and decide if the assumptions were reasonable. So we're allowed to make some assumptions here, right? We don't need to do it for each one, right? So let's see if we can come up with some equations. Is there any way we could deduce these 2 positions at the end? How are these 2 positions? How are they related to something in the problem? So when the police car catches up with it, let me redraw this. So when the police car catches up to the speeder, what can we say about the 2 positions?
You're gonna have the same position.
Exactly. So that's going to be one equation. That's going to be one of our equations, right? So we say these 2 are equal to each other, right? And we reduce these 2 variables to 1 variable now, right? Because it's the same. Now, since this is an estimate problem, we have to estimate the acceleration in this problem, right? So what's a reasonable acceleration for a car? I'm sure somebody's heard some numbers, how fast a car accelerates at such and such a time, or how fast it ends up going after a certain amount of time, like 0 to 60 in X amount of seconds. What's normally the seconds here? So how fast can a car accelerate to 60 miles per hour usually?
Depends on the car, though.
Well, reasonable. They said reasonable estimate. Yes, just give it in a range of values. Or just give me a number that's reasonable.
7 seconds.
That's reasonable. Yeah. I think that's kind of a slow car, maybe. But so here, so let's say it accelerates to 100 kilometers per hour in 5 seconds. It's a cop car, it's supercharged. It's about 60 miles an hour. So the acceleration is 100 kilometers. So what we say as our 4th equation, we just estimate it, right? 100 kilometers in 5 seconds. Right. This is the velocity in 5 seconds. This is our 4th equation. Right. There's only, sorry, there's 4 unknowns. Why did I write 5? 1, 2, 3, 4. Yeah, I counted T twice. I'm sorry about that. There's 4 unknowns, right? So we have 4 equations now. Now we can solve this problem. We can figure out t. We have 4 equations. There's 4 unknowns. We can figure this out. Right? So let's first put everything in SI units. So we need the units to be in the standard format for everything to work out properly. And to calculate the times properly. So let's convert the police car. Let me put a P over here, and into seconds, into meters per second. So let's do that. I'm going to erase this stuff up here. So, oh, that's not good. I'm running out of, how can I stop working all of a sudden? Okay. The acceleration of the police car is 100 kilometers per second, and it's in 5 seconds. So let's convert this into seconds. First, let's convert it into kilometers, into meters. So we multiply, it's 1,000 meters per kilometer, right? That's our conversion. And then we got to convert hours into seconds. So 60 seconds in a minute, and then 60 minutes in a second. So we end up getting 136. I'm sorry for writing so small. I'm running out of space here. I'll just start again over here. So let me do this calculation first. So we have 1, 2, 3, 4, 5 zeros. So this is 10 to the 5th meters per hour over 5 seconds. Now we got to convert this to seconds and then we would have, so there's 1 over 3,600 seconds and an hour. So then we have hours per second. And then we multiply through, seconds per hour. No, it's hours. All right. And we end up with, and then when we divide by 5, we end up with meters per second. So this is the acceleration of the car in seconds. Let's also convert this to seconds as well. We have the S, and I'm just going to write it down and use the same type of conversion method. And then it comes out to be 42 meters per second. Okay. Next, what we do is plug things in. So the fact that XP and XX are equal to each other at this point, we can express this as just saying, as just writing this. And this is equal to OS, right? So we're using this equation and combining it with those two. Now all we have to do is plug in the numbers. Or why don't we simplify it first? So let's isolate t. So we divide this by t, and then we divide this to the other side. So we end up getting VOS, V naught S over AP, right? And then this is our answer. And if we look at the units, let's look at the dimensional analysis. This is meters per second squared. And then this is meters per second. Can you, sorry for making it so small again. Meters per second. And if you look, the meters cancel out and you're actually just left with 1 second. So the units work out. And then when we actually do the calculations, it only takes 15 seconds for the cop car to catch up to it. Does this make sense?
I have a question.
Yes.
The 100 kilometers per hour, what, we just guessed that, or?
Yes, yeah. We guessed that on the current specs on a car. Car can go about 60 miles an hour in between. The fastest cars, not electric, are about 4 seconds up to 10 or even more, depending on how heavy the car is. So we guessed 5. Cop car can reach it in 5 seconds. A cop car is pretty fast, actually, and they're turbocharged usually. So about 5 seconds to 100 kilometers per hour. 100 kilometers per hour is about 60 miles an hour. So we just guessed it based on specs for a car. Now, does this make sense? Well, what is its final velocity by the time it catches up to that car? So let's erase this. Let's see how fast it's going at its when it finally reaches the cop car. I mean the speeder. So the cop car. Let's plug in the equation for the cop car. So at V is equal to 15. So V in this case is just, well, let me write VP. Here I'm just taking the derivative of this, bring it down. It's just this. I'm not explicitly writing it out. Just bring down the 2. These 2 cancel out. And then we're left with this. All right. Now when we plug it in, 15, and then we have an acceleration of, what is it, 5.6 times 15. Does this make sense? So that it's going about 84 meters per second. It's pretty fast, actually. And so in miles per hour, when we convert it, is 100 miles per hour, or 190 miles per hour. Was our acceleration reasonable in this case? If the car ends up going 100 miles an hour? No, it's not. Now, actually, it's not our acceleration that was off, but we made an assumption in the beginning. Or for these problems, we made an assumption. We assumed that the acceleration was constant and it didn't change over time. And that's very false for high-speed cars, because over time what happens is that the drag from the wind applies a higher and higher force. So the drag actually applies an acceleration to the car in the opposite direction than the drivetrain for the car. And this acceleration increases the faster you go. that's why you accelerate slower and slower as you go faster and faster. So it would actually take the cop car a lot longer to reach the speeder. Okay. I want to move on. We have an hour. We have a half an hour left. I want to try to get through the rest of this section, or this this part. So if we don't finish, we should finish this today. So, all right. If we don't finish it, I'm going to extend the homework deadline from Monday to Wednesday. Work on the homework sections that we did in class. And if you want, wait until we cover the rest on Tuesday to answer whatever other questions. Don't wait until Wednesday to do the homework. You'll kill yourself. And then I'll post the quiz later that night. If we don't.
And what time is the homework? The quiz, I mean?
I usually have the homework due at 12 noon, and then the quiz due by midnight.
We can access the quiz anytime.
Well, yeah, you can do the quiz anytime. Doesn't matter. But it's only available until 12 midnight, and then can't do it. And I can't extend the quiz. So if you miss it, you have to no. Jediah, it's on masterinphysics.com. Look at the syllabus. There's a course code they have to type in, and it's a pay website. It's like $70. It was $70, and you have to answer the questions on that. It's due Friday. Can somebody send them the course code for Master in Physics?
Sir, is the first quiz due this Friday or next Friday?
It's due this Friday.
I was asking because I ordered.
It's not up yet. It's not up yet. I'm gonna post it afterwards.
I ordered the book so I could get the access code from the book.
No, I provided it in the syllabus.
No, you need to have an access code to use the website. You have to get it from the book, or you have to buy it online. And
What access? No. To use the website, you have to type in the course code that I provided you. That
I know that, but you to use the website itself, you need to have get an access code from the book itself.
Okay. I think you could just pay for access.
No, it's because I ordered the book. It should have the access code in it, but didn't come yet.
I'm not aware of that. Everybody else was able to get to the website if they used the used copy of the book. I never heard.
But when you order the book new, you get an access code for the website with it. So that's a $300 book. So
yes. So okay. So when you order the book, you don't have to pay that $70 fee. I think that's what you're saying. Okay.
But his book hasn't shown up yet, I think.
Yeah,
Saying,
his book is going to be...
You get a free trial of the course, I believe. You get 2 weeks before you have to pay for it. So you should have access right now.
Okay.
If you don't, email me. We'll take care of it. So just let me know if you have any issues with that. But you should have a certain grace period before you have to purchase it. It's 2 weeks, if I remember. All right. Any other questions regarding Master in Physics or anything like that? Let's just draw the graphs for the speeder and the police. So what would the position function look like? So the speeder is going at a constant velocity, so it will the speeder will just be a straight line, right? Oh, sorry. This isn't so straight. Right? And the cop car would, since it's accelerating, it'll look like this. And this is the point where they cross each other. Let me draw it in black. And this is the point where they cross. Right? And then the way we did the problem, the velocity curve of the two, right? The way we assumed in the problem is that this is the speeder and this is the cop car, right? And as we saw, this is not correct. Really, what it should look like is this. So it'll experience constant acceleration at first because the wind velocity isn't that high, and then it'll actually start slowing down. And then what normally happens with a speeder is that they see the cop car and then they start to slow down themselves, right? So oh, let me draw this a little bit. All right. So they'll cross over here now. This is the, well, not the cross, they'll cross over here. The velocities will end up being the same at this point. Just because when the velocities are the same doesn't mean that they'll cross at the same point. All right. And then the cop car, now the cop car will start overtaking. See, at this point, it's not closing the distance between the speeder and itself. Only after it reaches this point where the cop car gets faster than the speeder does it start closing that initial distance down. Okay. Now I should make a note here. So this whole idea of velocity, it wasn't well understood. This constant acceleration or changes in velocity wasn't well understood until calculus. So Greek mathematicians had problems with this, right? So they had one issue, right? So this faulty logic would be, all right, let's say if I'm a runner and I'm racing a tortoise, it's going very slow, right? So I start running, right? I get up to my final velocity fast, which is faster than the tortoise, right? I close that initial distance down, let's say 100 meters, right? But in that 100 meters, the tortoise traveled a little bit further on, right? Then I close that distance down, but the tortoise has traveled further, right? Then I close that distance down, and the tortoise keeps traveling just a little bit further, right? So in essence, what they're saying is that the runner will never catch the tortoise. And this was a conundrum that they had. And here, what they were assuming was you're only dealing with finite time intervals. You don't have this infinitesimally small time interval. And once we introduce calculus and this idea that this instantaneous velocity at each point, this solves this problem. So they weren't able to mathematically describe this type of stuff before Newton, before Newton, really. They couldn't describe it that well. Because of these conundrums that they would run into. So it's quite interesting. All right, so the next thing we'll deal with is another constant acceleration problem. And this is and we'll be dealing with this throughout the semester, actually. So this is freely fallen object. So this is section 2.7. Now, so at any given location on Earth, in the absence of air, every object falls at the same rate, right? If you know this, of course it does. Gravity is the same everywhere, so it will fall the same rate. But people, especially in Galileo's time, who actually came up with this, it wasn't quite obvious because of air resistance, right? If you drop a feather in a ball, it'll fall at different rates, right? But once you remove the air, they'll fall at the same rate. So, so no matter how heavy the object is, it will fall at the same. It will accelerate at the same speed, and the speed is called is called g, and it is equal to 9.80 meters per second. So this is what it is on Earth.
Isn't it meters per second square?
Yes, thank you. Thank you.
No problem.
Meters per second square.
Is it 9.8 or 9.81?
In the book, they use 9.8. Usually, you use 9.81. I use it 9.81 elsewhere, but in the book, they use 9.80. So we'll just use 9.80. It simplifies everything. And then a lot of people actually just use 10 a lot of the time. So if you're doing simple calculations. And then in English system, in feet, it's 32 feet per second. So, and this is a good measure of gravity for everyday life, even as airplanes high up. Actually, so this gravitational constant changes based on the density of the Earth, so it's not actually constant everywhere on Earth. And also, the fact that we're spinning reduces this gravitational constant, depending whether you're on the North Pole or the South Pole. So that's why most rockets take off from the equator. Is because the effective gravitational constant is less there. And that's for later in the semester. But we'll just take it as 9.8. And so for freely falling objects, let's take a simple example.